Hello everyone. So in this lecture we will study about the electrostatic potential energy and electrostatic potential. So suppose we have a charge plus Q1 charge and we want to bring a Q2 charge from infinity to a distance r. Right? Now if we see, there will be a force on Q2 that will be in this direction, and that force is electrostatic force. E is here electric field due to the charge, right? So for bringing this Q2 charge from infinity to a distance r, we have to apply a external force in this direction, and this force, if external force will be like this, that there will be no net acceleration of this Q2 charge. So F external and this electric field will be same in magnitude but opposite in direction, right? Now there will be some work done by this F external force, and that work done will be stored as a potential energy. So this work done we can calculate F dot dr. F can be written into this force, direction is opposite, and when we calculate this, then it comes out K Q1 Q2 upon R at a distance R, right? So this will be the potential energy for two charges at a distance R. So simply we can say, if there is a system Q1 Q2 at a distance r, then potential energy will be this. So remember this formula, right? Now for a system of charges, suppose there is a system of three charges, so Q1 Q2 Q3, there are three charges. Suppose this distance is r1 r2, this is r2 r3, this is r1 r3. Then we'll put the potential energy will be for every pair of charge. So first of all Q1 Q2, U1 U2, फिर U2 Q1 and Q3 charge, then Q2 and Q3 charge. So U1 U2 will be K Q1 Q2 upon R12 plus K Q1 Q3 upon R13 plus K Q2 Q3 upon R23, right? So this will be the potential energy of this system. So for a system of charge, we will write the potential energy for every pair of charge, right? Now the potential energy is a scalar quantity and unit of it is joule. Remember, whenever you write the potential energy, put the charges with sign, right? So if charge Q2 is negative, then we'll put here minus the magnitude of the Q2 charge, right? Now for a charge, for a system of four charges, how we will write the potential energy? We'll do a simple question. Before that, we'll solve a simple question of two charge system. So here we are given two positive charges and they are located at a 15 centimeter. Then find the potential energy. So formula of potential energy is K Q1 Q2 upon R. R is here given 15 centimeter. So we will put in meter SI unit, that will be 0.15 meter. Q1 Q2 are given in coulomb and both are positive. So put all the values and solve, then we will find the potential energy of this system. Now the potential energy of four charges system in Q1, Q2, Q3, Q4 are given and they are kept at the vertices of a square of side 1 meter. So suppose this is the our square, its side is 1 meter Suppose this is the Q1, this is the Q2, this is the Q3, this is the Q4. So how we will write the potential energy? It will be written U12, U13, U14. Then due to Q2 charge, it will be U2, U3, U2, U4. Then Q3 charge, U3, U4. Right? Now write the all the terms. U1, U2 will be K into Q1, Q2. Q1 is 1 microcoulomb. That means 1 into 10 raised to power minus 3 microcoulomb. Right? Upon R1. R1 2. That is 1 meter. Right? U1 3 term लिखी, that will be K into Q1, Q3. Here Q3 will be written minus 3 into 10 raised to power minus 3 coulomb. And the distance between Q3 and Q1 charge is root 2 into side of this square, that is 1. So that will be root 2. Right? Similarly, other terms also can be written, and some of these all terms will be the potential energy of this system of charges. So I hope you have understand the concept of potential energy. If you have any doubt, then ask in the comment section. Next, what is the electrostatic potential? So electrostatic potential in an electric field is defined the work done in bringing a unit charge from infinity to a distance, that is called the electrostatic potential. Right? Now, at infinity we assume electrostatic potential energy, electrostatic potential all are 0. So suppose there is a charge plus Q. Right? Now we are bringing a unit charge Q2 from infinity to a distance R. Then the potential will be work done in bringing to this Q0 charge from infinity to R, that is called the potential of this charge. So this will be W external upon Q0, because Q0 is a unit charge, and W external we already calculated, that was K into Q upon R, right, into Q0 also, right, upon Q0. So if you simplify this, then this become KQ upon R. So we can write, due to a point charge at distance R, potential will be KQ upon R, right? Remember this formula now. Now what is the potential difference? So potential difference is nothing but work done. Potential difference in electric field is work done for bringing a unit charge from point A to point B, that is called the potential difference. So work done will be difference in the potential energy, that means UB minus UA will be VB minus VA, right? So this can be written VB minus VA equals to KQ, right? And this is for unit charge, so we'll divide by Q0. So this will become KQ upon RB minus KQ upon RA, or you can simplify this. So it will become KQ upon 1 upon RB minus 1 upon RA. Unit of potential difference is also same. So unit is volt over joule per coulomb. Also we'll see other units also. This is also a scalar quantity, right? So this is the electrostatic potential. Now, if electrostatic potential is path independent, what is the meaning of this statement? This statement says if we bring a unit charge from A to B from this path or from this path, the potential difference or the potential difference here, the potential difference will be same. So for both path, potential difference will be same. VB minus VA will be same. If we bring charge from infinity to a point, then it will become the potential. So that will be same, that will be independent of the path, right? Now potential due to a point charge we already calculated, that was the at a distance R, potential is KQ upon R. So we can derive the graph between potential and distance. This will be a hyperbola. So this will be like this, right? Now, potential due to a system of charges. So already we have written the potential energy due to a system of charges. So similarly we can write the potential also. So it will become like V1 plus V2 plus V3 and so on. If there are charges Q1, Q2, Q3, Q4 and so on. Suppose we want to calculate potential here, that if this distance is given R1, then the potential V1 will become KQ1 upon R, and if this distance is given R2, then the potential will become KQ2 upon R2. Similarly, the electrostatic potential energy, we will put the charges here also with sign. Remember this. If this distance is given R3, then similarly we can write the V3, that is K into Q3 upon R3. Similarly other terms also can be written. So potential due to a system of charges will be written like this. Now, potential due to a line charge or a charge cylinder also. So potential will be due to this, it will be minus 2k lambda into log that on base E R, right? This will be the potential due to a line charge. Remember this formula. If you want to draw the curve between log and between R and V, so that will be the logarithmic curve. So leave the graph here. Potential due to the charge circular ring, only remember the formulas. If you want to draw the graph, then you can draw easily. That will be the logarithmic graph. So due to a charge ring, suppose this is a ring, this is center, at distance x, if you want to write the potential, so potential will become here V equals to KQ upon x square plus R square, and it is very simple to calculate this. Why? This is the uniformly distributed charge, so you can take a small charge in it. Potential due to this, that will be K into dq upon, this is x and this is R, then this distance will be R square plus x square, the square root, right? So for every charge this will be same, and the potential will be KQ upon square root of x square plus R square. Now at center x will be 0, so V center will become KQ upon R, right? Now if x is very large than the R, then we can approximate this result. So V will become KQ upon X, right? That means for large distance we can assume this is a point. So remember this formula. Now, potential due to charge conducting sphere or cell of the charge. So for a conducting sphere, charge will be on the surface of sphere only. Suppose this is the positive charge, and this is charge Q. So the potential outside the sphere, suppose the radius is R, so outside the sphere at point P, distance R, potential will be, you can assume sphere as a point charge, that will be KQ upon R. At surface R will become the radius, so this will be KQ upon R. Now inside this sphere, it will become constant, and that will be the KQ upon capital R, because there is no charge inside this sphere, right? So inside the sphere, remember, potential will be KQ upon R everywhere. That means it will constant. If you want to draw the graph, then it will be like this. This is potential, this is R, then it will be constant till R equals to capital R, then it will be a hyperbola. Now, potential due to a uniform charge non-conducting sphere. So I'll write the formula, you have to remember this. Suppose this is a uniformly charged non-conducting sphere. For a non-conducting sphere, charge will be distributed over the volume. Suppose this charge is Q and radius of this sphere is R, then outside at point P at distance small r, it will be, we can consider it is a point charge KQ upon R. At surface it will become KQ upon capital R, but inside this sphere it will become KQ upon 2R cube into 3R square minus R square. If you want to write in terms of rho, then rho is the charge density, that will be the Q upon volume of this sphere, that will be 4 by 3 pi R cube. If you want to simplify this, then this will become, rho into R cube upon 3 epsilon naught into R, and this will become rho R square upon 3 epsilon naught, and this will become rho upon 6 epsilon naught 3 R square minus small r square, right? Now at center small r will be 0, so we center will be rho into R square upon 2 epsilon naught, and that is equal to 3 by 2 V surface. So it means at center potential is more, right? So now if you see the graph, remember this graph also, formula you have to remember this graph also. this is V, and this is R. So from 0 to surface at center, what will be the potential? Potential will be 3/2 V surface. So this will be the potential. Now till now potential will decrease and it will be in terms of this function, right? After this it will decrease like this, hyperbola, right? So this will be the VC, this will be the, and VC will be, if we write 3/2 V, then this will be the V. This is at surface, right? So graph will be like this, and this formula you have to remember. Now potential due to a hemispherical body. So potential due to a hemispherical body will be V equals to sigma R upon 2 epsilon naught, where sigma is the charge density per unit area for this hemispherical body. R is the radius of this hemispherical body. It is a constant value. Now potential due to a uniform charge disk. So suppose this is the disk and charge is uniformly distributed on this. Radius is R, charge is Q, then distance at distance X. Potential will be, and sigma is the charge density, sigma upon 2 epsilon naught x square plus r square का under root minus x. This will be the potential. And what was the formula for electric field? Sigma upon 2 epsilon naught into 1 minus x upon square root of x square plus r square. So this is the potential formula, and remember this formula, right? Now we will solve some question based on these formulas. So first is, a charge 2 microcoulomb is taken from infinity to a point in an electric field without changing its velocity. If work done against electrostatic force is minus 40 microcoulomb, then potential at that point is. So what is a potential definition? Potential definition is work done by the external force in a electric field bringing for a unit charge from infinity to a point. That is was the potential. So potential was the W external upon Q, right? Here Q is given 2 microcoulomb, that means 2 into 10 raised to power minus 6 coulomb. Now if work done against electrostatic force is minus 40, so work done is by external, it is done against electrostatic force, and we know the F external and electrostatic force are in opposite direction. So W external will be minus 40 microjoule, that means minus 40 into 10 raised to power minus 6 joule. Then the potential will be V equals to minus 40 into 10 raised to power minus 6 upon 2 into 10 raised to power minus 6, that means minus 20 volt. Now in this question, an infinite number of charges each equal to Q are placed along the x-axis. Suppose this is the x-axis and this is x equals to 0. Now one charge is put here, x equals to 1, and every charge is Q charge. This is x equals to 2, that is Q also, x equals to 3, that is Q also, right? So find the potential at the point x equals to 0 due to this set of these charges. So what will be the potential? V equals to kq upon distance 1, kq upon this distance is 2. Similarly you can write all other terms. So this will become kq upon 1 plus 1 by 2 plus 1 by 2, 1 by 3, 1 by 4. This is a series. This is a series. No. What? First charge is put at x equals to 1, second is x equals to 2, third is x equals to 4, and fourth is x equals to 8. So this term will be 4, this term will be 4, this term will be 8. Now you can see this is a series and this is a geometric series. Here kq, here a is 1, this is infinite geometric series, a is 1, and what will be the r will be 1 by 2. So sum of a infinite gp is a upon 1 minus r. So use this formula. A is 1, 1 minus 1 by 2, this will be 1 by 2, and if you solve this, then this will become 2 into k into q, right? So you can easily calculate the potential. Put the value of k is 9 into 10 raised to power 9, and value of q is not given here, so only in terms of q we can find the answer. Now, two tiny spheres carrying charges 1.5 microcoulomb. So q1 is 1.5 microcoulomb, that is 1.5 into 10 raised to power minus 6 coulomb, and the other charge is 2.5 into 10 raised to power minus 6 coulomb. Located 30 centimeter apart, that means r is 30 centimeter over 0.3 meter. Find the potential at the midpoint of the line joining the two charges. As spheres are the tiny, so we can assume this as a point charges. Suppose one is here q1, q2 is here, midpoint, that means this distance is 0.15, this also 0.15. We have to calculate potential here. So Vp will be k into q1 upon 0.15 plus k into q2 upon 0.15. If you put value of k, q1, q2, then we will find the potential at the midpoint. Now, in this question, what we are given? Calculate the potential at a point P due to a charge of 4 into 10 raised to power minus 7 coulomb located 9 centimeter away. So there is a point charge q, that is 4 into 10 raised to power minus 7 coulomb, and 99 centimeter, 9 centimeter away from this. Suppose this is P point. So P will be k into q upon 0.09. This 9 centimeter in meter will be this. So this will be the potential. Put the value of k and q, we will find the potential. In B part, hence obtain the work done in bringing a charge of 2 into 10 raised to power minus 9 from infinity to the point P. What is the meaning of this? That means we have to find work done. So work done, what will be the V equals to W external upon Q, right? So what will be the work done? Q into V, and V at point P. Point P is at 0.9 centimeter, right? So here Q, value of Q is 2 into 10 raised to power minus 9, and value of V at point P, it will be from here. So this will be the work done. Now point C, does the answer depend on the path along which the charge is brought? No. We know the potential is independent of the path, right? And here we can see also at point P potential will be the same. From which path you come, that doesn't depend. Now, relation between the electric field and potential. Right? So, relation between field and potential, as we have seen, VB minus V, potential difference is W external when we move from A to B upon the charge. This was the potential difference, and if we simplify this, then it will become delta V equals to minus E into E dot delta R. If you take modulus of this, then delta V becomes E into delta R, or we can write E equals to delta V upon delta R, right? So if we put equals to delta V upon delta, this is the formula, or you can write in vector form also. You can write E equals to minus dV upon dr. This minus sign shows that if we move in the electric field direction, then the potential will decrease. Or we can say electric field will be in that direction in which the potential decreases steep, right? So potential, simply remember, potential will decrease in direction of electric field. Right. Now, what is the equipotential surface? Equipotential surfaces are the surfaces where V is constant. Right. That means E equals to minus dV upon dr, and if V is the constant, then E will be 0. That means for equipotential surfaces, electric field will 0. Now, a charged particle moves a distance of 0.4 meter along an equipotential surface of 10 volt. Calculate the work done by the field during this motion. So, how we will calculate this? We know delta V equals to W upon Q. So, W will be Q into delta V, right? So W equals to Q is given 1.4 into 10 raised to power minus 3 coulomb. Now delta V will be with the 0 because this is an equipotential surface. So equipotential surface means potential is everywhere same on the surface. That means work done will be the same. So we can say for equipotential surface, work done will be 0, electric field will also be 0. Now potential energy in an external field, right? Suppose there is a external field E and the charge is here in this field. Then the potential is V, then the potential energy can be written like this, Q into V, that we know. So remember this formula also, potential energy Q into V, and work done will be same, U Q into V, right? Now if there is a system of two charges in external field, that means this is electric field and there is a charge Q1 here, the another charge is Q2 here, then what will be the potential energy? So how we will write this? potential energy due to this pair, that will be K Q1 Q2 upon distance between these charges, right, plus Q1 charge into potential at that point, suppose that is R1, right, and Q2 V of R2. This will be the potential of this system. Correction, the potential energy of this system, right? How we can explain this? Suppose there is an electric field E and we are bringing a Q1 charge from infinity to at a distance R1, then what will be the potential energy? Q1 into potential at that point, that is V R1. Now we are bringing the Q2 charge, then the from infinity to a point, then the potential energy will be due to the external field and due to the point charge Q1 also, right? So that's why the potential energy of this system will be written like this. Now we will see some important points of conductors. So first is, inside a conductor electrostatic field is 0. Suppose there is a conductor, when we apply an external field, then electrons will move opposite to this. So electrons will accumulate in this direction and the plus charge will accumulate in this direction. Now we know electric field lines starts from positive and ends at negative, so there will be electric field will in this direction. This is, suppose this is external, then there will be internal electric field here, and this electric field will be equal to external. That means this is 0. So inside a conductor electrostatic field is 0. Now at the surface of a charged conductor, electrostatic field must be normal to the surface at every point. Now if the electrostatic field is not normal at the surface, then what will happen? Suppose the electrostatic field is in this direction, then what will happen? Suppose electrostatic field is in this direction, then there will be two components. One will be the perpendicular to the surface and one will be the parallel to the surface. So this is parallel to the surface and this is perpendicular to the surface, right? Now this parallel component, due to this parallel component, at this point there are some charges. On those charges there will be a force, and due to that force charges should move on this surface, but that's not possible. That's why the electrostatic field will be in perpendicular direction only, right? So at every point on the surface of a conductor, electrostatic field will be normal to the surface, right? Now there is a question, which electric field line representation is correct for a conductor? First of all, it cannot be true, because inside the conductor there will be no electric field, so there will be no electric field line, right? Now the second, this electric field line is looking like entering from here and exiting from here, right? So this is also not true, because this is not perpendicular to the sphere, sphere, right? Now these are the electric field lines which join the center. That means these are the perpendicular electric field lines. That means correct option will be the D. You know, for circle and sphere, this is true. The line which are passing from center, that will be the perpendicular to the sphere or the circle. Now the third property, the interior of a conductor can have no excess charge in the static situation. So in static situation, inside the conductor, the charge will be zero. Inside the conductor, all charges accumulate at the surface of the conductor. That's why inside the conductor, field will be zero and potential will constant. Now inside the conductor, electrostatic potential is constant and it can be explained by E equals to minus dV upon dr. As E is 0, that means dV is 0, यानी कि change in potential is 0, that means V is constant. Now electric field at the surface of a charged conductor, it will be sigma upon epsilon naught into n cap. How we calculate this? We calculate this, suppose there is a small part of this conductor and that is a spherical element. We will take a spherical element and suppose charge density is sigma. Electric field due to this element will be in this direction and the vector ds will be also in this direction, right? For this surface, as electric field is perpendicular at the surface, so electric field will be in this direction. So for curved surface, if you write go slow now, that is E dot ds q enclosed upon epsilon naught, right? So if you write this, then this will E dot ds, that means E ds cos theta, q enclosed up will be sigma into ds upon epsilon naught, and this will become suppose this area is this whole area. This is for very small element. The whole area is delta s. Then we'll write here delta s whole area. Now this become theta. For curved surface, electric field in this direction and unit vector, area unit vector will be in this direction. That is 90 degree. That means this will become 0. And for this surface only, because here no electric field, here for this surface only we will write, and this surface for ds, n cap will be in this direction, E is in this direction, theta is 0 degree, so it will become E ds sigma delta s upon epsilon naught. And if you write this is E into delta s. Delta s the area of this element, sigma delta s upon epsilon naught. If you write electric field, that is sigma upon epsilon naught. That will be in outward direction. So for conductor at the surface, you can write the sigma upon epsilon naught electric field. Now in this question we are given ordinary rubber is an insulator, but special rubber tires of aircraft are made slightly conducting. Why is this necessary? So whenever a aircraft lands, then there will be friction and the tires are touched to the runway, right, or the path which was there. So that is called runway actually. So when the tires touch the runway, there will be some electric charge will generate, and for that aircraft rubber tires are made slightly conducting, right? Now the next is a bird perches on a bare high power line and nothing happens to the bird. A man standing on the ground touches the same line and gets the fatal shock. Why? So suppose this is the wire and bird is sitting here. right? So what is the potential difference here? 0, because this line has same potential. So potential difference here also same, here also same, so potential difference will be 0. Now if a man which is standing at the ground touch this wire, right, what will be the potential difference? Here the potential is different, and here the feet of this man is touching to the ground, so potential is different, so there will be the potential difference, right? That's why the man who is standing at the ground will get a fatal shock, right? So these type questions can be also asked in the exam, and there they will give 4 questions, 4 options, and you have to choose correct option. So in this chapter we have studied about the electrostatic potential energy, electrostatic potential, relation between potential and electric field, and now in next we will study about the dipole. So before ending this, I will compare the forces. So we have done a question regarding a gravitational force and a electrostatic force, and we have seen the electrostatic force was much greater than the gravitational force. Now gravitational force is only attractive in nature, but electrostatic force is attractive and repulsive also, and both are applicable for long range particles also. Now the nuclear force. Nuclear force is much greater than the electric force and gravitational force, and this is applicable for short range. So nuclear force, you know, we apply for neutron, proton, electron, neutron and electron also, right? Now last is weak forces, right? So weak forces are for short range, and they are, so weak forces, they are less than the Fn but greater than the electrostatic force and gravitational force. So they are, we can write like this: Fn is nuclear forces greater than all other forces, then weak forces, then electric forces, then Fg. Remember this, right? So in next lecture we'll study about the dipole.